Every day, we experience reactions involving the transfer of energy, such as cooking or flipping on a light switch. These simple actions are thermodynamic reactions because they transform energy into a different form. More specifically, thermodynamics is the study of heat, temperature, and their relationship to energy in a given system. To understand thermodynamics, we must first define a system and its surroundings. A system is a quantity of matter with a fixed identity. Systems include any objects or materials that are directly involved in the reaction. A reservoir, for example, is a system that contains water and a dam for water level regulation. The rocks, wildlife, and cars driving on the road above are part of the surroundings because they are not directly involved in maintaining water levels. Can you think of any other examples of a system and its surroundings in your classroom? While you explore the classroom, let's try to understand 3 different systems involved with thermodynamic reactions. The first system is called an open system because it transfers both matter and energy to the surroundings. Such a transfer is observed when water is converted from a liquid into gaseous steam. As the steam is released into the surroundings, heat energy is also emitted. A closed system is the second type of system. It allows for energy transfer, but not matter transfer. Let's modify our boiling water example by adding a lid to the pot. Energy now takes the form of heat, while matter, in the form of steam, cannot escape. The third system is an isolated system. In the isolated system of a thermal container, neither energy nor matter can enter or exit. These 3 systems are incorporated into the 3 laws of thermodynamics. The first law of thermodynamics, otherwise known as the law of conservation of energy, states that energy can neither be created nor destroyed. However, energy can change forms. Hydropower clearly shows energy changing forms without the creation or destruction of energy. When a dam is closed, kinetic energy is unavailable due to the absence of water flow. But when the dam opens, rushing water provides energy for the system. Energy is not added to the system, but is converted from potential to kinetic and then to electric. The second law of thermodynamics states that the entropy of any isolated system increases. The system of your room will increase in entropy, or disorder, until you are forced to clean it. Thus, energy must be exerted in order to decrease the entropy. The third and final law of thermodynamics states that the entropy of a system reaches a constant value as the temperature approaches absolute zero. In other words, all processes cease as the temperature of a system reaches absolute zero. This property is shown by adding cold helium to an already inflated balloon. As the cold helium enters the balloon, the molecules lose energy to collide with one another, and thus the balloon deflates. On the other hand, when warm helium is added to a balloon, the molecules collide and react more frequently. These 3 laws of thermodynamics apply universally, but let's look at a system to thoroughly grasp the concept of free energy. Free energy is defined as the amount of energy in a system that can perform work when temperature and pressure are constant. In order to classify reactions, we'll focus on the free energy change termed delta G between the final and initial states in the system. 2 types of reactions are classified based on their free energy change. An endergonic reaction, such as photosynthesis, absorbs free energy as a reactant. Thus, delta G will be positive because the system gains free energy. But during an exergonic reaction, such as cellular respiration, free energy is released as a product. In this case, delta G will be negative because the system loses energy. So the next time you are performing an everyday task like cooking food on the stove, cleaning your room, or even sitting in class, think of the energy transformations happening around you. And remember that most of these transformations can be attributed to thermodynamics.